Hello everyone. In this video we will see how we implement SDK application development by using Xilinx SDK. First we will get the hardware file, description file from Vivado. Then we will import it to SDK by means of hardware platform import system. Okay, further we need SDK, run the SDK. And after that we are actually going through various iterations of the design flow. We need to set the workspace, means the place where we are going to store all our project files. You can give any name you like. Okay, once you create a workspace, all your files will be stored there for that given project cycle. So I'm giving my workspace as a name. Click OK, then go for OK. It would take some time for SDK to run. Okay, we got the welcome screen. Then in order to actually import the hardware, we have to open file, new, go for others, and here select the Xilinx tab and go for hardware platform specification. So why we are going for it? We have to import the hardware definition file which we have generated from Vivado. Okay, in order to develop the application. For that we are going for next, and we have to give the name of the project. I am going to give it Minized SDK, and we have to give the source where we have stored the HDF file, hardware description file obtained from Vivado. I stored there zsystem wrapper.hdf. This HDF file is nothing but a kind of a zip file which actually contains all the required file to say what the system is actually containing. Okay, now close the welcome screen. Then you will be seeing the C++ perspective in the SDK. It's based on Eclipse open source IDE. You can see, you can go for open perspectives tab for going for different perspectives based on your requirement. Okay, for now we go for C++, and the open tab is system.hdf, means it's a definition file which gives a description of the hardware. Here you can see the Minized details, and the address map is also given there with a list of the peripherals. You can see the address map for processor and the Bluetooth, GPIO, PWM. This PWM is actually a custom IP which we have developed, and this acts is GPIO. USB, QSPI, all these peripherals, they're accessed in terms of memory. You can see there is a base memory and there's a higher address, means from base memory to higher address you got this. Here there is a S_AXI, which means it's a slave AXI. So what does it mean? It means it refers to some blocks in PL itself. Okay, I'll show that actually design, but most of the time software designers don't have the accessibility for the hardware design. Okay, here you can see the UART block, this actual Zynq system itself, and reset block, various GPIO blocks, the PWM block itself, and the axis BRAM above that. Okay, so what actually this HDF file is giving is, it gives all the details necessary for the software designer to work on the system without knowing how the hardware designer built the system itself. Okay, this slave axis, you can see there is a axis interconnect block there. The Bluetooth is connected to Zynq by means of this axis interconnect. It actually acts as a medium. It is responsible for generating that memory mappings. So for using this memory map from this region to use this region, you can access Bluetooth. Okay, if you see slave axis, it means it is present in PL itself. That's it. And bottom there you can see the IP blocks present in the design. A lot of IP blocks are there. Okay, and their versions. So actually this file is actually giving a big picture perspective, and this bitstream file is actually stored there with the .bit extension, just system wrapper, and this init.html, this file is you can tell it as a kind of a data sheet which contain all the memory maps, memory addresses of each and every register of the PS itself. So you can see it's a design summary. Down there it's a MIO table. MIO means multiplexed IO, which refers to PS block. So which pins are used for which functionality, it has given all these things. And the DDR memory information, clocks, what is the CPU frequency, all the information, and the various FPGA frequencies, and you can see MIO registers itself. So all this data refers to only PS registers. Yes, clock registers, PLL registers. You can access each and every clock register by means of these addresses. These address, their read or write type, their reset values, all the every data is given there. But using that data is difficult. There is a init.h file. The init file is used when you are starting any system. It's kind of used for starting first stage bootloader. You will be seeing bootloader for running system, similar like that. And the components of this header file, you can see UART frequency, the same thing we have seen in the HTML file and that HDF file. These are the required things, initializations needed while starting the system. All these are done by init.c file. Okay, and there is a GPL file, not much different with the init files, but just for a general purpose licensing. And this MMI file, which is used for referring the block RAM mapping. We are not using block RAM for this projects. Okay, and this is the table giving functionality of each file. This is actually, as I told you, used for first stage bootloader. Init.h is nothing but a header file, and init.html, it is a kind of a data sheet. Okay, it can do a lot of information. This init.tcl file, This performs on initializations when using SDK in JTAG mode, such as in debugging. So I'll open it, the tickle file. Okay, yes, it got a lot of memory locations. Why they are used? They are actually used to help in debugging. Okay. Then GPL, as I told, this is identical to init.c, but with the GNU general public license. So you can see, if I open gpl.h and init.h, you can see the contents both are same. Both the contents are same. Okay. Then you got drivers, which contains tickle file for generating parameters for custom driver. I already told you PWM is a custom driver. You can see that here. Yeah, it got all the custom drivers we are using, and this source file got the source files C file and H files. .h files. Tickle commands stored in data folder. These are used for accessing the custom drivers, which are not developed by Xilinx, user defined. Then Xilinx XML file and hardware handoff file means when you are changing your project, the details, and the wrapper.bit file. This is actually the bit stream, which is actually necessary when you are programming the system. It actually configures the PL. Okay. It's a very important file. And MMI, memory map info file for the BRAM. Then okay, now we'll be seeing this development flow. We have imported the hardware platform. The next thing we need to do is generate the BSP, board support package, which contains the libraries, provides the APIs, drivers, all the necessary things to develop the application. BSP is actually an integral part. It actually makes our life easier. I'll show. The C++ file or C file we create interacts with BSP. BSP interacts with hardware. So it kind of abstraction layer we use in order to talk to the hardware. Okay. As I shown, there are a lot of low-level details we need to deal in order to work on the systems. So this abstraction is very necessary thing in order to develop huge applications and target independent of the any board or manufacturer. So BSP is a kind of ideal thing which provides APIs to talk to the hardware. As I shown, the BSP is a middle layer and the hardware is on the bottom, application resides on the top. Application calls the BSP by means of API, and BSP interacts with the hardware by means of drivers. So it makes our life easier. We develop only application. Here also you can see the red dotted line shows the BSP parts, 3 layers of BSP. You can see the low level, this stacks, all these things, low level drivers, HL, hardware abstraction layer drivers, safety service layers. Applications now on the top will interact with BSP by means of interface API. Okay, and they can talk such a way, and they can get information like low level information like ADC values and how a pin, whether it is on or off, whether we blink an LED or not, whether how you can access a SPI, whether you interact through CAN protocol. All these things can be possible. So if you see the Xilinx Minized architecture, the PS interacts with memory, peripherals. Here in that, while interacting with peripherals, we kind of use BSPs as a middleman to interact with them, and they actually kind of form a bridge between those. Here you can see, for a given system, maybe it got a Ethernet, QSPI, IOT, timer and INTC. So it got some specific hardware blocks. Based on these hardware blocks, we generate a few files which are necessary for those blocks only. Okay, so it's kind of think it as a modularity. Okay, so a board support package generates headers or library for the hardware in that system only. So for that we need to go for open new BSP, give the name for the BSP and select the standalone itself and go for finish. Okay, then here you can see there are a lot of libraries available provided by Xilinx. You can actually go and select if your application needs some critical functionalities, or a lot of powerful libraries are there. For example, you can go for RSA. It's something related to cryptography. Okay, now we don't need all these things, but you can see standalone nothing but a simple low level software. It's different from Linux kind of OS. And you can see these configurations you can actually configure. Here there is a mistake, it needs to be UART 1. You can change that value, so you can actually control what kind of peripheral is to be used for what purpose. You got that much flexibility. Okay, and here you can see the drivers. You can actually select whether you have to use this driver or another possible drivers. Here I can select BRAM or another generic or none for that BRAM controller, but we have to go for BRAM specific things only if possible. There are a lot of, for all peripherals there is a driver there. You can see that for UART, USB, yeah, and here it is actually necessary when you are going to debug the board support package. For now we go for OK. You can see BSP block is generated and the file structure hierarchy there at the bottom. So this MSS file, system.mss, gives a description of all the details required for using this BSP. I will maximize it. You can see the drivers and the documentation also given there. So if you want to see how you can interact with a specific driver or a specific peripheral, you can go for the documentation, or you can actually go in a more robust way, the import examples. Let's go for import example for Bluetooth UART. Select this hello world example and click OK. You can actually see the working thing, and if you can actually change small trivial details for your project. Okay, and if you observe, the application at the bottom interacts with the BSP, yeah, just at the top and middle, and BSP interacts with Minized SDK hardware. So here you can see the hierarchy. Yeah, superb. Okay, that's what I actually shown here. The application contacts through the API the hardware. Okay, let's see what it contains. Application got binaries. This binary file is used for programming the PS system. similar to, whereas this bitstream file is used for programming the PL. That's it. It got include files, source files, which contain maybe C files. Yeah, yes. See the functions. Okay. If you see the, okay, we'll see the C file. Just for an idea, you can see at the starting line, hash include x parameters.h. If you go for the definition and go for it, click open declaration. You can see this is actual file, and if I hover mouse on it, it got lot of macros defined. If I hover mouse, you can see the location. It contained in a standalone BSP. Means I'm actually using a file given by BSP itself. So you can actually see PS Cortex 90 include. You can see these are all the header files for various peripherals, drivers. You can see xparameters.h, which contain all the parameters like frequencies, addresses, base address of the peripheral, all these things. These are generated by BSP automatically. Okay, and based on using these functions, you can see Bluetooth is actually a complex program. But you can say few lines of code is used. Just using BSP, these functions, we actually simplified our work. Yeah. Okay, for now we close it, and these are the actual import examples. And okay, that's it. If you want to go for documentation of specific peripheral, you can go for through documentation and PS7 Cortex got all library files. These are the library files that are generated by libgen, that is by the SDK based on our hardware. So it is unique. So this is a BSP. Now I am going to remove it, delete. For now it is not necessary. Okay, it is now in my workspace. So I delete the entire project on disk. Okay. Yeah. Now if you see the flow, now we got the BSP. Now the next thing is we develop the application using the BSP. That's it. So for developing application, we first go for file, new, application project, then give our project a name for application. I'm going to give it my application. Okay, and here it selected create new, but I already got a BSP, so select use existing BSP 0, go for next, and here you can see there are templates. These are actually, we actually used one of the template, Bluetooth template. That's also a template. So you got a TCP stacks template, memory test, RSA, DRAM, a lot of templates. For now we go for empty application itself. If you need, we can actually import or add into our project. Go for finish. Okay, that's it. You got a source file. Yes, we got includes. Good. And that's it. Okay, thank you. We'll see how to run in next video. Bye.